Hello everyone. Now we have to discuss problems on coupled circuits. We have to discuss gate and previous gate and ESE problems. So this is the first problem. The equivalent inductance seen at terminals A and B. We have to calculate the equivalent inductance. Right? And we all know that before starting the problem, first we have to get the current direction. This is the current direction. See, based upon the current direction, given that this is the dot point, right? This is another dot point. This is another dot point. So this is given that this is L1, this is L2, this is L3. Clear? And what about this 2 Henry, 1 Henry and 1 Henry? See, in this the current leaves, right? But coming to this, in the second coil, the current enters from the dot, right? Therefore this 2 is what? Minus M. Like that, between coil 2 and coil 3, entering. Therefore this is plus M. Between this, between 1 and 3, here it is leaving, here it is what? Entering. Therefore this is minus M. That's it. Very simple problem. Given L1 is nothing but 4 Henry, L2 is what? 4 Henry, L3 which is also 4 Henry. Clear? What about mutual inductance between 1 and 2 which is equals to what? Minus 2 Henry, right? Or you can write minus M, or you can write which is equals to minus M. Like that, what about 2 and 3 which is positive, right? Which is 1 Henry plus M. What about 3 1 which is what? Minus 1 Henry which is equals to what? Minus M. Therefore L equivalent is what? All are connected in series, right? All are connected in series. Therefore L equivalent is what? L1 L2 plus L3. Now M12 is what? See, we have negative sign, minus 2 into M12, right? See, between M23 we have plus 2M23. Coming to this 2M31. What is the formula? L1 plus L2 minus 2M, right? That's why L1 plus L2 plus L3 minus 2M plus, here it is positive, here it is negative. Therefore we can substitute the values. Simple. L1 total equivalence is what? L1 plus L2 plus L3. See, between this 1 and 2 we have minus M, therefore minus 2M. Between this 2 and 3 we have plus M, therefore plus 2M. Between this 3 and 1 we have what? Minus M, therefore minus 2M. Therefore 4 plus 4 plus 4 minus 2M12. 2 into M12 is what? 2, right? Or you can write, let us remove this, it's better. Okay, 2 into M23 is what? 1. So M23 is positive, right? Minus 2 into this is what? 1. This one gets cancelled. Therefore this is gets cancelled. Finally, what is the equivalent inductance? That is 8 Henry. The answer is what? 8 Henry. You can solve more number of problems, then only you will have better idea about the concept. Okay, here I am providing only one solution regarding this series connection of equivalent equivalent inductance. Then you have to solve more number of problems based upon this problem. Next problem is the impedance seen by the source. Just now we have discussed, right? In the circuit in figure is given by, he provided the turns ratio is what? See, this is what? 1 is to n. 1 is to n. Second case. And what about this is what? Z. this is load, no problem at all. Okay, let us assume this is Z1. Okay, this is Z1, this is ZL. We all know that listen carefully, for ideal transformer input impedance here provided the turns ratio is what 1:n, therefore 1 by n square into secondary impedance, right? This is for ideal transformer, but he provided some impedance in the primary, that is 4 plus J2, sorry 4 minus J2. Therefore, by including Z1, the input impedance is simple. Z input, which is equals to what? Z1 plus 1 by n square impedance of the secondary. Very simple one. That's it. If we don't have this Z1, obviously Z input is equals to what? 1 by n square into impedance of secondary. Therefore, what we have, which is equals to, this is what? 4 minus J2 plus 1 by n square 16. Impedance of secondary is what? 10 at an angle, given that 10 at an angle 30 degrees, right? So Z input, which is equals to what? 4 minus J4 plus we have 0.54 plus J 0.313. So from this Z input is equals to what? 4.54 minus J 1.69. That's it. The answer would be C. Next problem, this one. See, in the circuit shown figure, it is found that the input AC voltage and AC current are in phase. In phase means what? There is no phase angle between voltage and current. Therefore, the power factor is unity. Means the circuit is under resonance, right? Where M is the mutual inductance between the two coils, the value of K and the dot polarity. We have to calculate the value of K and the dot polarity of the coil P and Q. Okay, we have to calculate the dot of this, whether it is here or here, we can calculate. So given input AC voltage and current are in phase, only at resonance condition, right? So given input AC voltage and current are in phase only at resonance condition, therefore that is XC, which is equals to XL. That's it. XC, which is equals to XL. From this we can write what is XC. He given that, see, this is what XC component, XL is what? Here we have what? J8. Therefore we can have mod Z12, which is equals to mod J8 plus J8 plus what we have? We can have what? 2M. Why it is L1 plus L2 plus 2M? That is, this part is what? This is what? L1 plus L2 plus 2M, because all are connected in series. Since assume plus M, because we don't know exact value of dot position, right? assume plus m. That's why we have what? L1 plus L2 plus 2m, right? Therefore, what we have? Minus j12, which is equals to j8 2 in place of m, k into square root of L1 L2, right? So minus j12, which is equals to j8 2 into, what is the value of k? Given that we don't know, so okay, we don't know. This is j square 64. So from this what we have? 12, which is equals to 8 plus 16k. Therefore from this k is equals to what? Minus 4 by 16k is equals to minus 2.5. So k is minus, right? Here k is equals to what? Minus 2.5. Here minus sign represents what? Hence coupling will be opposite. Therefore dot will be at q and k is equals to what? 0.25. K is equals to 0.25. Option C is the correct answer. K is equals to 0.25 and dot at q. Next problem. If an ideal transformer has an inductive load element at port 2 as shown in figure, the equivalent inductance at port 1, given that, see, n:1 is nothing but the turns ratio. We all know the relation. What is that? We know that, very simple problem. V1 by V2, which is equals to square root of L1 by L2, right? Given that which is equals to n by 1, right? This is the given data. From this, L1 by L2, which is equals to what? N square by 1. From this we have to get inductance at port 1, therefore L1. Therefore L1, which is equals to what? N square into L. That's it. Very, very simple problem, right? This is GATE 2006 problem. N square into L. That's it. Next problem. The resonant frequency of the given series circuit. Know that Fr, which is equals to 1 by 2 pi root LC. Given that all answers in what? Hedges only. Therefore, we can use this formula. Fr is equals to what? 1 by 2 pi root LC. Heads. Therefore, what about here? He provided M is equals to 1 Henry, L1, L2 like this, C. So, this is the value of C. This is L1, this is L2. Therefore, we have to get L equivalent first. L equivalent is what? Is it plus M or minus M? Plus M only. Plus M. Why it is plus M? C. That is entering. Current enters at both the ends, both the dots, right? L equivalent is what? L1 plus L2 plus 2M. That's it. Which is equals to L1 is what? 2 plus 2 plus 2 into M is what? 1. Which is equals to 6 Henry. Given that C is equals to what? 2 farad. Therefore, Fr, which is equals to 1 by 2 pi root L is what? 6 into 2, which is equals to 1 by 2 pi root 12. Therefore, Fr is equals to what? 1 by 4 into 3. 4 pi into root 3 heads. That's it. Answer would be B. Very simple one, right? Next, the inductance matrix of a system of two mutually coupled inductors shown in figure 1. Then this is figure 1. Okay, this is the matrix for this figure 1. this is figure 2, which are connected in series. See, from this and this, obviously m value should be minus m, clear. When the inductors are connected as shown in figure 2, the equivalent inductance of the system is given by what? Very easy one. So 5 minus 4 minus 4 7. So based upon this, what we have? All are connected in series, right? Therefore we can write, see, from this what we have? V1 V2. Between these two we have m plus m. So by using KVL, first we have to get loop 1 equation, loop 2 equation, then we will have matrix. Solution. By using frequency domain, we can write directly. This is what? J omega L1. This is what? J omega m. Why only J omega m? Because m is positive, right? J omega m. This is what? J omega L2. That's it. This is what? I1, I2. Clear? Yeah. Given m, which is equals to minus 4, we can write that matrix. Given, what is the matrix? 5 minus 4 minus 4 7. 5 minus 4 minus 4 7, right? Then compare this equation, so this matrix with this matrix. Therefore m, which is equals to minus 4, L1 which is equals to 5, L2 which is equals to 7. That J omega is nothing but common for every inductance. Okay, therefore we all know that he wants L equivalent, that is L1 plus L2 minus 2m. Why it is minus 2m? Because with respect to, we got the information from figure 1, that is L1 is 5, L2 is 7, m is nothing but minus 4. That's it. So based upon that information, we can get the equivalent inductance from this figure 2. From this we have minus m, therefore minus 2m, right? Therefore L1 is what? 5 plus 7 minus 2 into minus 4, which is equals to what? 12 plus 20 Henry. L equivalent is what? 20 Henry. And he wants extra information. Yes, that's it. The answer would be 20. Yeah, next problem. The voltage equations for the following coupled circuits we have to calculate. See, here M12, is it positive or negative? This is obviously negative. See, here the current leaves, here the current enters. Obviously M12 negative. Between M12 leaving, entering, this is negative. So between 2 and 3 entering, this is positive. Clear? Here entering, here it is leaving, this is negative. Clear? Only M23 is positive, right? Only M12 is what? M12 is positive or negative? See here, sorry, M12 is positive. See, current enters, right? This is positive. Current, see, the current direction is what? Like this. I thought the current is like this. Sorry, here M12 is positive. Clear? Like this, leaving. Between I2 and M23 is negative. Sorry. First we have to see the current direction. See the current direction here. I3 is what? Leaving. I2 is entering, therefore between 2 and 3 negative. Here I1 is entering, I3 is what, leaving. M13 is nothing but negative. Clear, right? Let us say this is figure A, figure B. Okay, let us say this is case 1, this is case 2. From case 1, from case 1, so from case 1, first we have to write V1, which is equals to what, L1 di1 by dt minus, what about mutual inductance between M12? Why it is negative? See, here current entering, here the current leaves, right? M12 di2 by dt. Clear? Like that, V2 which is equals to L2 di2 by dt minus M12 di1 by dt. So this is what, now we can write V1 which is equals to j omega L1 I1 minus j omega M I2. V2 which is equals to what, j omega L2 I2 minus j omega M I1, right? This is time domain, this is frequency domain. Clear? Next, coming to case 2, only M12 is positive, remaining 2 are negative. Case 2, simple, V1 which is equals to L1 di1 by dt plus positive M12, right? di2 by dt minus between M13 di3 by dt completed. What about V2 which is equals to L2 di2 by dt plus M12 di1 by dt minus M23 di3 by dt. Like that, V3 only L3 di3 by dt. Just you have to know which one is positive, which one is negative, then only you can write the equations very easily. M23 di2 by dt minus M13 or M31 di3 by dt. That's it. Next, in frequency domain, what we have, j omega L1 into I1 plus j omega into M12 into I2 minus j omega into M13 into I3. Like that, V2 which is equals to what, j omega L2 into I2 plus j omega M12 into I1 minus j omega M23 into I3. Just by seeing this, we can write j omega into L3 I3 minus j omega M23 into I2 minus j omega M13 into I3. That's it. This is what, time domain, this is what, frequency domain. By seeing the coupled circuit, we can able to write the loop equations in time domain analysis as well as frequency domain analysis. That's it. So next, find the equivalent circuit and net inductance. See, this is very important observation. Here the sense of winding is starting from here, right? For example, this is dot, current enters, right? This is leaving, again it is enters. Now it is what, sense of winding changes, right? Enters, now leaves. That's it. So from this, here from this dot current enters, but from this is the sense of winding, right? The current leaves. See, the current leaves from this dot. Only we have 3 coils. From here to here, 1 coil, and from second coil he provided at this. This is on the another sense. See, it is from back side of the coil, but here you can have, see, listen. Now it's okay. This one dot, here another dot, entering from this, leaving from this. Again we have another dot. See the sense of winding starting from this. Okay, only we have 3 dots. So from this, what is the equivalent circuit? So based upon this dot convention, based upon sense of winding, we have provided the dot conventions. That's it, right? Between these two is M12, right? Between these two, M23, like that. Between this 1 and 3 we have M13, right? Given that this is L1, see, this is L1, this is L2, this is L3, this is what, M13, this is M12, this is M23. Therefore L equivalent, this is the equivalent circuit, right? This is the equivalent circuit. Therefore L equivalent is what? L1 plus L2 plus L3. See, M12 is what? Entering, leaving, negative, clear. What about M23? Leaving, entering, negative. What about 13? Entering. This is positive. That's it. Minus 2 M12 minus 2 M23 plus 2 M13. So from this, L1 is what? Say 1.5 plus, actually this is XL, right? No problem at all. He provided the answer in terms of XL only. If you provide the value of omega, we will get the value of L, right? This is what? J 2.5 plus J3 minus 2 into M12 is what? Into J2 minus 2 into M23 is what? This is also negative, right? M23 is what? Say 15 plus 2 into M13 is what? J12. Sorry, this is 1.5, not 15. This is 1.5 only. So finally what we have? We got L equivalent as J6 ohms. That's it. The answer is what? J6 ohms. Next, obtain equivalent circuit for the following coupled circuit. Means we have to get the electrically equivalent circuit for this circuit. Very simple. See, we have modified this. That's it. Okay, only we have to modify this. Let us say, right, this is L1 completed. Next, this is L2. From this we can, that's it. Sorry, here we have That's it, right? Next, from this, that's it. Is there any? Yeah, plus minus V1 AC quantity. We all know that this is I1 plus I2, clear. This is R1, this is R2, this is L1, this is L2, right? Between these two, this is C. The sensor binding is what? Starting from here. Here the sensor binding is starting from here. Therefore, dot point is like this. Okay, between these two we have what? M. That's it. This is the electrical equivalent circuit for the given circuit. These are the very important problems. Sorry, here I1. That's it. Like this you have to get the electrical equivalent circuit for the given coupled circuit. So these are very important problems based on this coupled circuits. Okay.